Hello, you guys, and welcome to the show. Today we are finished with the chapter of quadratics in the A-level math course, or maybe further math course as well. So that's typically year 12. We have been going through the quadratic functions, their graphs, so the parabolas. We have been correctly reviewing the quadratic formula. And today we will use a past paper question to consolidate this. And it's a nice question because it's a creative one. And let me see if I can share my screen. Going to my PowerPoint. I hope it's visible now. Should be. Right, so the demo lesson will then deal with the following question. So n cubed plus 3n2 plus 2n, that has to be proven to be a multiple of 6, no matter the n integer value. And I just want to state the objectives of the lesson. So basically, it will be to practice algebraic manipulation in this context. But then other sub-objectives or like some other things will be practiced. We will like aim at revising factorization, the quadratic functions, the formula to factorize, but then also touch the divisibility rules and just generally our number sense, which is always good to do in math, to experience its beauty and the way it's just grateful to work with. So we will also identify two strategies to use when we're stuck. And that's always good to strengthen our studying technique. The exam question review will only be done with questions, so no answers to you as a student. You will have to come up with the answer. I'll just guide with questions. And we will put careful attention, yeah, a lot of attention identifying and trying to close the knowledge gaps we might stumble on. So without further ado, my question is, what is your first reaction when you see that question? So n cubed, 3n2, 2n, multiple of 6. So I would listen to your reactions. What do you think you would do? Yes, and the feeling of being stuck probably and just not really know what to do is normal. I would say that this is an abstract expression, and maybe the first thing to do is just try it for a few n values. So how about if you plug in n equals 1, n equals 2, and n equals 3 to actually see that your formula here, sorry, your expression gives and returns a multiple of 6. And that makes you, yeah, not fully like done, absolutely not, but quite satisfied, probably more, willing to cooperate with the hard parts, I guess, just by confirming that this is correct. So these values show we're doing something right by trying to show that. And the question is how to go on next. So you have this expression, the stop one. You want to prove something about it, multiple of 6. You would have to process it in some way, right? And what is really the first thing that comes up here? If you're a year 12 student, already a GCSE student, would probably think, well, there's not much to do but factorizing, right? So there is an n we can take out, and really we cannot hold off with that because that's the only way to process this expression. And it's not like we cannot we're not going to process it. We have to make this expression progress to an equivalent expression, right? And so that's an equivalent expression, but it doesn't say much about divisibility by 6. That's clear. So the question is what to do now next, right? And because we've just done the quadratic formula and the quadratic functions and the factorization, we should be able to see that come into play to factorize this polynomial, right? That's a polynomial. It's only got n values, so integer values, but still, um, that's a polynomial. That's a second degree expression. So the question is how we go on from here. So that would be back to you. How do you process this one further? What can you do with it? And if the answer is given by you as a student, then it's fine. If it's not, then we'll have to revise this, which I think is probably meaningful for a lot of people. So just to remember, if I start by expansion, right, expanding, so first polynomial and then the first degree polynomial, it will just give me a quadratic, so with degree 2, right, polynomial of second degree. Now, if I go this way, I'm expanding. If I go this way, I am factorizing, right? And right now, I'm having this situation. I want to work my way back to the two brackets that will together multiply to this result. So just notice that, right, if you're having, so sorry, this would be a blue number, ideally. 12 is really this one. I wanted to make it, yeah, I don't know. My PowerPoint didn't save the changes. So I guess what I was trying to point really is that this number, which I put here in red, the 7, is the sum of these two numbers that are in your factorization bracket. While 12, that should be here in blue, is actually the product of 3 and 4. That's what you get as a constant. You get these two multiplied, right? So if you were to hit 3n plus 2, right, that's what you want, right, in the end. So when squared plus 3n plus 2, what you need is two brackets, and you do want your two numbers here, like the roots, very roughly said. It's actually the minus the roots with a minus sign. But let's say like these two constants have to multiply to 2 and add up to 3, right? So two numbers multiplying to 2, adding to 3. It would be just simply, right, multiplying, giving 2 is just 1 and 2, and the sum is 3. So that's fine. It would be n plus 2 and n plus 1. Giving us basically the factorization of the polynomial, quadratic polynomial we have here, right? Now, if we're not able to guess these two numbers, I just want to make sure we revise the standard method for factorizing a quadratic polynomial. And it's basically the coming one. So it would be using the discriminant, right? Because this expression will be factorizable under the condition of the sign of the discriminant, right? So remember, we've gone through that in class, right? So it's positive, then okay, you have two distinct roots, and the factorization is possible this way. What happens if it's equal to 0, if your discriminant is null? So you will have two identical roots. And so let's call it x0, okay? So the factorization will be x minus x0 times x minus x0, so that will be squared. And then times a before, yeah? Mind the a before that. Many times you do get a factor before, so just make sure you have it there. And then, yeah, the last criteria just popped up here. When the discriminant is negative, factorization is possible in the complex set but not here in the current step of the curriculum. So this is to say that we can always factorize, and if we put, let's say, n squared plus 3n plus 2 and call this a, b, and c, then we could just use this formula. We will find a positive discriminant with one root which is -1, one root which is -2, and that will give us the factorization that we found earlier. So anyway, back to business now. That's it. So here, our full factorization gives us taking out the n first, and then splitting it into n plus 2 and n plus 1 as a fully factorized expression of this cubical start expression here. So my question is again to you, what is the coming step? Because now we have to relate this to divisibility by 6, right? So how is this going to add up? How is this going to help us now? How come this is divisible by 6? So that would be back to you then. What do you observe? Do you like comment to yourself by any means with these two numbers, n plus 2, n plus 1, which is the smallest one of those? It's n, which is the biggest one? N plus 2. What does n plus 1 stand for? It's a number in between these two. So hopefully we are able to see that these are three consecutive numbers, right? So this is then, that makes it the product of three consecutive numbers. And if we just have a look at how this looks like, we could actually try it through examples just to see whether this always brings a number that's divisible by 6. That would be interesting to test. Then again, something to do when we're stuck, right? To just kind of identify the pattern. So of course, I do have 6 and 12 that are multiples of 6. And if my three numbers include 6 or include 12, then the question is very easily solved. So I will put myself in the worst situation where the three numbers are picked somewhere. So I'm just moving my picture here. Yes. So we'll be just choosing a situation where these two, the three numbers that are picked are strictly like located between 6 and 12, just to pick something and then see what happens. So we could either pick 7, 8, 9, or 8, 9, 10, or 9, 10, 11, right? And then, of course, if I would pick smaller numbers or bigger numbers, then, the next set will include a 12. So that's then just a non-starter. What happens with the first choice and the second choice and the third choice? Are those going to give me a multiple of 6? Back to you. You will have to figure that one out. Is there by any chance a way for this number to be a multiple of 6? What's 6? Like, what is included in 6? What is its structure in terms of products? What do you have included in 6? In terms of, yeah, really factors. We should think about 2 and 3, right? Multiply giving 6, okay? So this is an even number because of the 8, right? So the product will be divisible by 2, which is then good. It's not enough. If I have to get something divisible by 6, I have to make sure the number is divisible also by 3, right? It has to be divisible by both. And now here I actually have 9. That saves me because 9 is a multiple of 3, right? And then the 8 will provide the divisibility by 2, the 9 by 3, and that's fine. What happens in the next choice? 8 is still there. 10 is also there, so I'm having two numbers who are even, but also 9 is in the middle of my choice. And then when I move just below 12, before I hit 12, I'm taking 9, 10, 11. I will also find one even number, so not two, but one. The 11 is a prime number. It doesn't help me in this context, but the 9 will provide divisibility by 3. So the question is, why does this work? And basically, it's because, so that's back to you. How come this is working? If I look at myself strictly between two consecutive multiples of 6, between these five numbers I'm choosing, I'm always going to get a product that's divisible by 6. Because of these two numbers, so one is even, one is a multiple of 3, and then these two next time, and then next time it will be these two, right? Now, here's the kicker. I will always have an even number in three consecutive numbers I'm picking, right? Because every second number is even. And now every third number is also a multiple of 3, right? So if I'm picking 3 at random, there will always be a number that's in 3's times table. Um, so if we go here, like that's interesting. Sometimes when you have arithmetic exercises, kind of just mind that. So multiple of 2 would be no, yes, no, yes, no, yes, and so on. Multiple of 3, no, no, yes, no, no, yes, no, no, yes. Multiple of 4 is no, 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 yes, no, 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 yes to every fourth, right? So if you would formalize this within an exam, you would just put clear the way you factorize your expression. You would notice, bring to attention that this is the product of three consecutives, as every second number is even and every third is multiple of 3, then this product will always contain at least one even number, if not two, and then one multiple of 3, right? And that's why it will always be divisible by 6, right? So let's see if I can just add in another virtual resource. I just wanted to show you guys how this looks like in GeoGebra, right? Right, yeah, that's it. So, hey, we'll pretend this is not in. So we'll type up our function, right? We go to GeoGebra, we start here, and we go, okay, so f of x is equal to x squared, so plus 3x plus 2, right? And I make GeoGebra plot my curve. So if we would be talking about quadratics, we could actually use also this resource to confirm that we have the two roots we were talking about, -2 and -1, which turns them to plus when we put the factorization, like when we set it up. We will also see that the function looks effectively as a parabola, look in graphical terms. So the graph is a parabola. It hits positive values outside the roots, so before -2 and after -1. And between the two roots, it hits negative values. So yeah, that's also like a useful resource when working with quadratics. And that's what I would use then to kind of visualize how the quadratic functions behave. Of course, if you were to remember that if you were to put a minus, that will split the shape of the swap or invert the shape of the parabola, and you will have a smiley like that's a sad face, right? So the factor before the x squared determines the shape, like the glad shape or the sad shape of the quadratic graph or the parabola. And that would be it for me. Let's see, I could just stop the sharing to go back to the screen here, to the main screen. I just really want to thank you for your attention. I enjoyed the lesson and I hope you did too. And we'll be in touch. Anything, just feel free to reach back out to me. Thank you very much. Bye bye.